What's up? So this is going to be a really short chapter. We're just sort of going to dive right into it. And what this chapter does, it's easier to show you. So this chapter, it deals with constrained motion and, whoa, and how Lagrange can, like the Lagrangian approach can deal with it. So in my own note-taking skills, this was the dopest thing Lagrangian approach could do. And so what it does was it took on constraints and it didn't even break a sweat. It didn't even bat an eye. It was like, yeah, and so that's really what this section and then the rest of the chapter focuses on, is that it can do this amazing thing. So this section just really goes over like the simple form of it where it's a pendulum. So the pendulum's constrained motion is done by that string and where it's fixated. So the pendulum can swing back and forth like I've drawn there. And it just can't move in such a way that the string won't let it. And as long as we're not going crazy, it won't move like inside the string boundary. It'll just move around the length of the string. So we're going to write that down kind of mathematically off on the side of the picture there. So the constraint on its motion is that the length of the string is going to be equal to the square root of whatever x it's at. Wow, it doesn't like me. It's going to be the square root, whatever x it's at. Wow, it's fighting me. Okay. Plus this squared plus whatever y it's at squared. So we're going to rearrange this so it has y. So y is going to be equal to the square root of L squared minus x squared. So y is going to be our dependent variable here, or yeah, our dependent variable here. So that's why we want to solve for it in that equation when we constrain our motion. The next thing we want to look at is the kinetic energy of the system. So the total kinetic energy here, it's of course going to be equal to 1/2 mv squared, which in this case is going to be 1/2 m times whatever the length is, and then however that theta value changes with time. So the time derivative of the theta squared. And then we're also going to square lambda, because that'll, or not lambda, the L, because that goes along with how, that's basically how the derivative of theta works, is it's paired with L. And then, so for the potential energy of this system, we're going to use mgh because gravity is going to be acting on it. That's what's keeping it in the pendulum sort of sway of things. And another way to write that is that height is going to be equal to mg times 1 cosine theta. So that's some basic trig function there. If you want, you can figure it out, or you could just trust me. But I'm going to go through this pretty fast because it's really simple. So what then happens is that we take our Lagrange, which we know is equal to t minus u. And since we know those two values, we're going to say that it's equal. We're going to know that it's equal to this. 1 minus cosine theta. All right. So from there, we can just take the Euler-Lagrange equation that we know. So I'm going to write that in blue. If you don't have this memorized already, it's probably a really good thing to get memorized. So we're going to take it we're going to take the Euler-Lagrange in respect to theta, because theta is going to be the part that changes. So our length kind of acts like the r in polar coordinates from the section before, but it's not going to change because we're not changing our string, so we don't have to worry about it. So this really only has one part we have to worry about, and that would be theta. Okay, so now that we have this written down, we're gonna actually do it. So the derivative of the Lagrange with respect to theta, it's just gonna leave us with this part. The other theta is the theta dot. So we end up with mgl sine theta. Everything else is a constant, and it just goes away. And then we get the time derivative of ml squared theta dot, which we get from this component right here. And once we take the time derivative of this, we see that it is equal to ml squared theta dot dot. And then that's so this combined with this is our equation of motion for the pendulum. And that's really it. That's how quickly Euler-Lagrange can deal with something as simple as a pendulum despite its constraints. So that's honestly the entire video. That's it. And then the next few chapters kind of deal with it a bit more in detail with some more complex problems.